The world we are living in is analog. Nowadays, advanced signal processing is performed on computers or specialized hardware which is in a digital world. Thus, we need conversion between these two worlds, the analog to the digital converter. The Shannon-Nyquist theorem states that input signals to be sampled need to be band limited and that for perfect reconstruction, the uniform sampling rate applied must be at least twice this bandwidth. Our goal is to pre-process the multiband signal in such a way that we can sample it at a rate much lower than the Nyquist rate of the original signal. The system consists of two main parts. First is the smart sampling card developed by our lab, and the second is a set of mathematical algorithms that reconstructs the original signal, and we want perfect reconstruction. We started with a MATLAB code for a sub-Nyquist system to prove this concept. And then we transferred the theoretical approach into praxis by constructing the modulated wideband converter MWC and implementing the reconstruction system. Here we can see the general overview of the implementation of our algorithm based on National Instruments hardware and development software LabVIEW. The first part, our smart sampling cards, followed by a low-rate digitizer and then 3 FPGA cards for signal reconstruction. The input to these cards come from a splitter which connects to two RF sources in our National Instruments chassis, and the outputs, these four output signals, are going to an A to D converter in the chassis, and we have here two LVDS cards which provide a link between two cards. Behind these three cards we have our cards with the FPGAs which perform the original or the complete algorithm. I'm now going to demonstrate the workings of the MWC. We have here the hardware. On this side we have the analog board with its input and its four outputs, and on the other side we have the digital board. We have here an output signal where we can see the PI of t, one version of the PI of t. As you can see, the PI of t is on the scope, and you can see here this series of pulses which have the periodicity between these two signals. I'm going to input two frequencies into the MWC which are generated by this Tabor signal generator. One of the frequencies is at 218 MHz and is an AM modulated signal. The other frequency is FM modulated signal at 246 MHz. We are seeing those two signals up here in their time domain. I'm now going to connect the input of the MWC to the splitter which combine the two RF signals, and on the other side I take one of the outputs of the MWC to go to our frequency analyzer. As we can see here, after I connected the frequency analyzer to the output of the MWC, one of the channels, I see here the spectrum on this point around 16.6 megahertz. I see one of the peaks of my Dirac comb, and from there on I see the two combined signals. This is the FM, which is the very wide signal, and somewhere about 1/3 into that signal I see my AM signal superimposed on this. So this demonstrates that we can move the signals from many 100 megahertz down into a range between 0 and 20 something megahertz. We also can see that the amplitudes of the original signals were quite similar, but after moving those signals down, they have two different amplitudes. The FM is much lower in amplitude than the AM signal. This is one of the effects we are using for reconstructing a later state. On the left-hand side, I have a section where I can select my frequencies for each of the carrier, my modulation type, and also other parameters of the modulation. When I start the acquisition program, at the top I display the time domain. In the bottom I display the frequency spectra, and I can see here the spectra of my FM signal, and I can see here as a peak the spectra of the sine wave. If I change the frequency slightly, only by 1 megahertz, I will see that the spectra moves at the next exposition cycle. So it moved, and the same way if I change the spectra of the sine wave, it will move. Additionally, I can have here a save. We first implemented our reconstruction algorithm with MAT script. Here I have the frame construction part, and here I have the algorithm of the OMP part. We could take the data from file, and when I'm running it, I get in these the slice boundaries and the middle frequency, and I get here the spectra of this reconstructed slice. The same way I have here for a second slice the boundaries and the reconstructed spectra. You can see here that here's a sinus frequency, and on this side we have here AM frequency. If I'm changing the input file, and I can also change the number of elements of samples I will take from the file. I restart again, and it takes now a while until he has processed all the samples, and I have here my second file. I have here a reconstructed FM, and down here I have again a reconstructed sinus signal, which is in those slides. I'm now showing you the implementation of the algorithm in LabVIEW FPGA. This is actually showing the frame construction part. I'm having here a variety of complex multipliers which are summed together in order to give me the elements of my frame matrix. I'm going over to the overall screen. On the top left hand I have the input as I get it from tape. I can select which of my 4 input channels I want to display here. On the right, on the upper right, I have one of the reconstructed channels. On the lower right I have the other reconstructed channel, and below here I have several numbers giving me information about the way through the system. I'm selecting my input file, I'm starting the program, I'm showing the new input, and I'm showing the new slices and the new output. This would be a sinus signal up here, and here the reconstructed signal is the AM signal around here in this area. I can select back to the signal we had before. Start shows the input signal and the reconstructed FM and the reconstructed sinus, which was overlapped in the input signal.